this auditorium about the history of quantum mechanics, because Cambridge has played an immense role in this, the development of quantum physics. And quantum physics has really been, let's say, the Enlightenment, can be compared with the Enlightenment for physics. So before quantum mechanics, basically nothing was understood about matter. We didn't understand why matter was hard, why many things in matter we had no understanding whatsoever. But then suddenly quantum mechanics was there, and many things became clear. And actually, together with my wife Céline, we just wrote a popular science book on quantum mechanics. My wife can explain it much better than me. That's why we are here with two people. But anyway.
Yeah, for those who don't know Frank, Frank is quantum physics professor here at Cambridge University. I'm his wife, but beside that, I'm an author, translator. I do impact producing and all kind of science popularization. And as Frank said, we wrote this book together, but for us, because for a scientist, it's not because you know everything about a certain topic that it's so obvious to write it down in an accessible language, and that's how we got married.
But anyway. But today is about 100 years of quantum physics.
Yeah,
so exactly 100 years ago, let's say the defining moment in quantum mechanics happened, and we'll try to kind of give you an idea of what this is.
So as Frank said, until 100 years ago, there was a whole series of questions on which people had no answer. Like why, when we hug a tree, why, when we sit on a chair, why don't we sink through it? Why don't we disappear in the tree? Why is mother hard? How comes the sun keeps on burning? How old is the earth? Where is this periodic table of Mendeleev coming from? And where are color? How comes that things have a color? What is the mechanism behind the thing as color? There were no answers on these questions, but quantum mechanics provided the answer on all these questions. So the interesting question is, of course, what exactly happened then 100 years ago? Where did the quantum revolution happen? Well, it's on two fronts simultaneously. On the one hand, we have Helgoland, which is a very small island in the north of Germany, an island without trees. And on the other hand, in the Swiss Alps. Our two protagonists of today are Werner Heisenberg and Erwin Schrödinger. Heisenberg was highly allergical to pollen, so that's why in Heligoland he was really good, because there were no trees, as I said, and he could perfectly work there. And Schrödinger was finding himself in the Alps, and there, independently from each other, they found their theory that they both look completely different, but they are actually,
effectively equivalent, but
they give the same predictions. And so these theories look like this. As you can see, they're completely different, but they are fundamentally comparable. And if you look well, you can see that they have both something in common, which is that H with H bar, and that is Planck's constant.
Planck's constant is something very small. And that's why it took so long for people to understand that this played a role, because you have to have very good experimental kind of apparatus to see this quantum. So this quantum is basically some basic unit, and this is a discovery that Max Planck made in the year 1900 and changed everything. Okay? So suddenly, what Planck effectively said is that you cannot zoom in ad infinitum. So before quantum mechanics, people thought, okay, you can always zoom in and you will always be able to go further and further. But this h bar, this very small constant, says if you reach that scale, then you kind of reach the smallest scale. You cannot go further, you cannot go smaller anymore. At that smaller scale, things change. You have to kind of get a complete different description of what happens. There is a smaller scale where entirely new physical laws take over. And that's where the name quantum is coming from. So when people in finance talk about quantum jumps, it means very small.
Or quantum leaps. Quantum leaps.
Anyway.
And also quantum physics, quantum mechanics, it's a synonym. Both means exactly the same thing. So, but what we have to remember now, that if we talk about quantum, it's the smallest scale. You cannot go smaller than this. Now, let's make a little exercise. What do you think that would never have existed should the Schrödinger equation not have been found?
Discovered.
Or discovered. So it's things that we all use in daily life. We are constantly surrounded by things that without quantum mechanics would not have existed. Do you have any idea? Applications?
Exactly.
Smartphone, exactly.
Yes. Transistors, of course, yes.
Full of transistors. Yes.
It's
Cats, quantum cats.
Okay.
Smart watches, if everybody, if somebody has one. So, well, we will see now the most important applications.
So of course, we already talked about
the transistors.
The transistor is actually something that would have been completely impossible. So it's probably the most disruptive discovery of the 20th century. And it's a pure quantum product. Without a good understanding of the Schrödinger equation, people would not have been able to engineer this. Okay, so the people that engineered the transistor were only able to do this because they understood very well the Schrödinger equation and the application of the Schrödinger equation to many electrons in a metal. So the person who was the definitive person that discovered this was Bardeen, and Bardeen is one of the most famous quantum physicists. So this is a pure consequence of quantum mechanics, of the understanding of that Schrödinger equation that was discovered 100 years ago. Of course, there's much more. Solar panels is effectively the same thing as transistors. This is a purely quantum mechanical kind of thing. So there's many more examples, of course, like lasers. Lasers are absolutely amazing. They run everything that we send, all the information we send around in the internet is based on lasers. And the history of the laser is actually extremely interesting. So it was Einstein. Einstein was completely engulfed in trying to understand the relativity theory, general relativity theory, and he wanted to have a break. So for one day he said, okay, let me think about light. And on that one day he actually discovered the basic principle of the laser. This is around 1917, 1918. And then it took actually 50 years for people to make a first laser. Then it took many more years for kind of developing this in a technological product. But you see that these are the length scales at which we're talking about. Okay, so there's the discovery, then actually making it takes 50 years, and then there's all these things. So this will kind of come back and forth. So this quantum mechanics is, so there's lots of things that are understood, but before you can actually make use of them, this takes a long, long time. But there's many more examples. Okay? MRI. MRI is actually an absolutely fascinating thing from the point of view of quantum mechanics. What happens when you're in an MRI machine is that basically your hydrogen, so all your spins in your body, so you have lots and lots of kind of hydrogen atoms, and then the hydrogen atoms, their spins, and all these spins are effectively in a Schrödinger cat. They are all pointing up and down at the same time. That's what the machine does. So you're kind of really in a superposition when you're in an MRI machine, and this superposition of having this up and down together is actually what allows you to visualize somehow these things. Atomic clocks, GPS, the person who said this would have been completely impossible without the understanding of quantum mechanics. So what is the driving force in GPS is not sending the signals, but having an extremely accurate clock. Okay, you need a clock that is extremely precise, but is also exactly the same, it doesn't matter where it is. And that is one of these things that happen in quantum mechanics, is that if you're going to a smaller scale, all particles are indistinguishable. We'll come back to this. This is one of the most important principles in quantum mechanics, and that means that every clock is exactly the same. Okay, it's perfectly reproducible, and that's a consequence of this smaller scale. If the smaller scale would not be there, it would be impossible to create two objects that are the same, but quantum mechanics allows you this, and allows you to make these extremely precise clocks that indeed drive basically GPS. Atomic energy. So there's also kind of course, this has good, but there's also bad sides. If you kind of come up with amazing discoveries, there are automatically also kind of side effects there. But we will not talk about this today.
Now, where does the quantum story really begin? For that, we have to go back to the year 1900, so the turn of the century. And that's not really a coincidence, because at all levels, things were happening there, also at the level of culture, of literature, of philosophy, of psychology. People were turning back to the essence, to the core. They were to the inner world, to mysticism. There was this search for authenticity. There were characters who fall apart in 1,000 persons. It was really a very interesting period, also at the geopolitical level, but what also in music. But what interests us, of course, is what was happening in science. Now you have to know, in that period, the classical theory of Newton was the reference. That was really the standard. And then people believed actually that, Newton, Maxwell, and Boltzmann. But in that period, people really believed that all laws were known. Everything had been discovered. So would you think then of studying science, people would really say, but you're crazy, everything has been discovered, there's nothing new anymore. And they also believed that space and energy could be divided ad infinitum. So there was not yet the idea of this quantum. So people believed that an apple could be cut in ever smaller pieces until Max Planck came along, and he assumed, but what if there is a smallest scale? And that changed everything.
Indeed, because there was actually an experiment that was in violation with the laws. And that is, of course, the amazing thing of physics. In physics, there's no alternative realities, alternative truths. You have an experiment that has to be kind of validated. And if you have a theory that is in correspondence with an experiment, you say, okay, there's a good chance that this theory is correct, but if it violates it, you have to discard it. So in physics, there is no alternative, there's just a truth. And people actually, especially in Germany, were very interested in understanding light better, because they wanted to measure better light bulbs for many applications. And what they had realized is there was something of a mystery, that if you kind of try to understand how much light there is, if you warm up somebody and you kind of try to see what are the frequencies in a certain, as a function of the temperature, then there was something that did not fit. Okay, so the electromagnetic theory of Maxwell was in violation with an experiment, and nobody had any idea of how to solve this. And then Max Planck realized that maybe let's make some mathematical, he wanted to do some mathematical trick to get results that were in accordance with the experiment. And for this, he introduced exactly this Planck constant, this very, very small number that we talked about before. And what he said is, let's assume that the waves, the electromagnetic waves, can only have very specific amplitudes. Okay, they can have amplitude 1, 2, 3, 4, but nothing in between. Okay, so if you kind of have a string of a violin that vibrates, there's only very specific levels of that string that are possible, and anything in between is not possible. Of course, this small. He basically says that energy is quantized. Okay, that the energy of a wave can only have some definite values, namely some integer multiples of some basic. And using this trick, by kind of assuming that indeed these amplitudes of these waves had to be quantized, he was able to completely explain this black box mystery, this mystery about these frequencies. Okay, so he said energy is quantized. But people did not really pay attention, because they thought, okay, this is just a mathematical trick.
But this makes it a little bit more clear. So the non-quantum world, you can take every energy every possible level. In quantum, it's every energy that is possible. But in quantum, you can only stand on certain rungs and nothing in between. And that's the same with quantum. So everything is quantized. It goes by steps, and it's not a continuum. But the thing is, with Planck, it was so much in contradiction, this idea of a quantum. There was so much in contradiction with everything he was standing for. That is the physics of Newton, that he thought, as Frank said, it's just a trick to make it work, but it can impossibly be true. Later it would seem to be true, but nevertheless. So, and then 5 years later, there was the first one who took this theory of Planck serious was Albert Einstein.
So Albert Einstein was really a rebel. So he really kind of took this idea of Planck and said, no, but this is not just a mathematical trick. This is actually saying something about physics. It really basically tells that light consists out of particles. So this fact that these waves or these amplitudes are quantized, they can only have some specific values. He took this as a hint that light actually does not consist out of waves, but consists out of particles. And this is, of course, a very strange thing. People all assume that light consists out of waves, and then suddenly Einstein says, no, you have to take this seriously. Actually, this theory of Planck implies that light consists out of particles. And these particles, we call them photons now. And actually, he went much further. He said that everything that vibrates consists out of particles. He also did this like for specific heats of materials and so further. So he really kind of stood. But this was a hugely important kind of step, a conceptual step, that saying, no, it's not a mathematical trick. It says something about the physics, something very, very physical And of course, we are already immediately in this paradoxical world of quantum mechanics now, because how can something both be a particle and a wave? And that's this duality that will that we still don't really understand in quantum mechanics, but it is the basis of everything.
And this theory was also, he found it himself also much more important than his famous EMC², because at the end it led to much more further breakthroughs. And it is also the theory for which he got the Nobel Prize. So here you see Einstein together with Planck. Then, in the meantime, the experimental physicists didn't remain idle neither. We go now to Manchester, where there was Ernest Rutherford from New Zealand. He was doing a very interesting experiment. Namely, he was bombarding atoms with helium atoms. And he noticed that most of these atoms were just, they went through the atom, and a very small amount were bounced back. So he came to the stunning conclusion that all the mass of an atom had to be concentrated in a very tiny spot, which we would call then the nucleus of the atom.
Before that, actually, people assumed that an atom was something that was smeared out. And if you have something like an atom is pretty big, and the mass is just spread out everywhere. And if you send a very small particle through it, then, well, it would just go through it because it's like a pudding. Okay? But then you have this very small thing that goes through it, and from time to time it's bounced back. And of course, this was a complete puzzle, and he realized, okay, the only way I can resolve that puzzle is that almost all the mass is concentrated in even a smaller thing, and if by coincidence somehow this small particle that I sent through is bounced back, it's because it hit exactly this nucleus. Basically, he said that indeed 99.999% space is empty, because if you look at an atom, somehow the size of the nucleus on this atom is much, much, much smaller than the complete size. Okay? So space is almost empty, but in the center of your atom there is this nucleus that is very heavy, and all the mass is concentrated. Okay, that was the only possible conclusion for that explained his experience. By the way, Rutherford, of course, after that became world famous. He came to Cambridge and founded Cavendish and many others. But well, not founded, but became a professor here. But Niels Bohr.
You can see that I placed him a little bit lower, because apparently theoretical physicists are a little bit lower in the hierarchy than experimental physicists.
Don't believe what Céline says. This is not
just by hearsay. But so Bohr, he was a postdoc of Rutherford, and he had the epiphany by understanding that electrons turn around the nucleus in orbitals, so not wherever they want, but in these pods, and they also are quantized. So the orbitals that go around the nucleus cannot have the energy they want. No, it goes by jumps, or it's energy 5, or energy 10, or energy 15. This again, which means that the orbitals are quantized.
And indeed, again, the H bar appeared there. So you have this tiny, tiny nucleus, and then very, very far away from this, you have this cloud of electrons. And so Bohr realized, he said, okay, this is a particle. An electron is a particle that is moving around the center like a planet, but it can only follow very, very specific trajectories. And these trajectories are such that the energy, again, of that electron is quantized in the same way as Planck said. Again, this is like a mathematical trick. Nobody understood what that meant.
Okay, let's summarize. So we had Planck saying that energy is quantized. Then came Einstein saying that, but in that case, light also consists of particles. And then there was Niels Bohr who said orbitals are also quantized. So electrons are particles. The next person in the row is Louis de Broglie, who was a French prince. He lived in Paris, and you can say it.
So Louis de Broglie made an extremely important statement. So he basically had worked during the First World War as an engineer, and he knew everything about waves, and then he basically said, yeah, but the only consistent way of understanding, of interpreting what Bohr said, is to say that electrons are waves. So this is exactly the opposite of what Einstein did. No? So you remember, light consists out of waves, and then Einstein said, but the only way that I can understand the experiments is by assuming that light consists out of particles. And here it's the opposite. Bohr said, have these particles that go on these orbits, And Louis de Broglie effectively explains the thing by saying electrons are not just particles, they're also waves. Okay? And that there must be some wave, there must be some equation, some wave equation that explains the thing. So every particle is a wave. And he introduced something that is actually the key in understanding quantum mechanics, and that's called the de Broglie wavelength. Okay, so basically he says that every particle is a wave, but it's localized. It's a wave packet, so it's not a wave that extends to infinity. It's a wave that is localized in space. And it has a certain kind of width, and that is called the wavelength. Okay, so the particle can never be completely localized in one space, on one point in space. It's always a little bit spread out. Okay, and that, how much it is spread out is the de Broglie wavelength. And this wavelength turns out to be larger the colder you make the temperature, or the smaller the mass you take. So if you have a particle of a very small mass, it will have a very large wavelength. If you cool something down, the wavelength will increase. Okay, and that's the key in understanding now quantum mechanics. Okay, so whenever you have a system of particles and their de Broglie wavelengths are larger than the distance in between them, then okay, you have waves, you will have something like interference effects, and that's when quantum mechanics kicks in. Okay, so when do you need quantum mechanics to describe a system of many, many particles? It's when the distance between the particles is smaller than the de Broglie wavelengths of the particles themselves. Okay, so every particle is a wave, and then you can see this if you have waves and these waves start overlapping, of course they start interacting with each other. You can have interference effects like you see in any wave. Okay, so let's kind of make this a little bit visual. Okay, so I have a system of particles, and this is the temperature. And let's cool the temperature, and let's see what will happen. Okay, so cool the temperature, and you make the temperature colder, so these particles become more and more wave-like. You have to describe them by larger and larger de Broglie wavelengths, and at some point these things start overlapping, and these particles completely lose their identity. Okay, the only way of describing the whole thing anymore is as one big wave. And that's exactly when quantum mechanics comes into play. So you cannot describe these things anymore. You cannot say this is particle one, particle two. No, the only thing that makes sense is to describe the whole thing as one big wave. Again, that's exactly why quantum mechanics is so hard to understand. It's not about individual particles. These particles have waves and they overlap, have lots of, well, the technical term is that they are very much entangled, and you can only describe this in a holistic.
So it's not because at a certain moment there was quantum physics that classical physics of Newton was not valid anymore. It's depending on what is the scale you are studying. So both go hand in hand.
Indeed. So for example, so as I said, the smaller the mass, the larger the de Broglie wavelength. Okay, an electron is something very, very, it doesn't weigh much, it has a very small mass. So the electron always has a very large de Broglie wavelength. And so you cannot understand anything about electrons without quantum mechanics. Because in a material, all the waves of the different electrons, they actually overlap. That's why to understand matter, and it's all governed by the electrons in your material, this is a pure quantum effect. But if you want to describe, let's say, the trajectory of a football, okay, this has nothing to do. You don't need quantum mechanics for this, because this is just one particle. The wavelength is extremely kind of small, and there's no point of even kind of thinking about quantum mechanics to describe the trajectory. Okay, so it's not because you have quantum mechanics that classical is not true. It all has to do with scales. It all has to do with what is the function of the temperature, or what is the de Broglie wavelength of the particles that you're interested in. Okay, but of course, if particles are waves, there should be an equation that describes their motion. Okay, so if you say I have particles or waves, that's the statement of de Broglie, but what is the equation then? People, especially here are also people like Rayleigh and many people here in the UK, they had kind of discovered and written down all the possible equations for waves. But if you say that the particle is a wave, then there should also be an equation for it. And that is exactly what happens 100 years ago. Okay, so 100 years ago in 1925, Erwin Schrödinger effectively wrote down this equation, and this is the equation that tells you how this wave, the motion, or somehow the equation that describes how the wave changes as a function of time. Okay, so this is basically this is probably the most important equation in the whole of physics, because it's amazing how much is described with this. Okay, so everything in quantum, everything about matter, as you will see, all these examples I gave about transistors, but anything about matter can only be explained by understanding and basically solving this equation. And who was the first one to really kind of do this? Who was basically the person who formulated quantum mechanics in the way we know it now? This is Paul Dirac. And Paul Dirac is one, of course, a fellow here in St. John's, always lived here in Cambridge, was an extreme genius, but he was also a bit strange. And maybe it's interesting to read a quote of him.
And then more serious. So Paul Dirac, I quote him, "I do not see how a man can work at the frontiers of physics and write poetry at the same time. They are in opposition. In science, you want to say something nobody knew before, in words which everyone can understand. In poetry, you are bound to say something that everybody knows already, in words that nobody can understand."
So you see already the duality there. But Paul Dirac was really the first one to understand quantum mechanics, and he wrote the standard textbook that is still used today. So one of the very first things that people realized with what can you do with the Schrödinger equation is completely understand where this periodic table is coming from. This was something that experimentalists like Mendeleev had kind of discovered that there's some kind of regularity in this, but nobody had any idea where this was coming from. And you solve the Schrödinger equation for some electrons, you kind of start manipulating these equations, and immediately somehow the structure of the periodic table was coming out. So this was, of course, one of the very big successes of quantum mechanics. It explained, it was also kind of the proof that quantum mechanics was the right kind of theory. But what is a quantum wave? Okay, so is it something, it's certainly, the interpretation of this is still completely open, and this is actually the biggest source of all the confusion about quantum mechanics. What is the interpretation? What does that mean that a particle is both a wave and a particle? Okay, what is the interpretation? How do I have to kind of see this? Is this particle actually everywhere at the same time, or how do kind of I have to interpret this? And indeed, somehow it turns out that the key in understanding this is information theory. It turns out that it's a very, very big leap, but that quantum mechanics is about information, it's about probabilities. It's not, this wave is not a physical wave. It's not a wave that you can touch, it's not something that you can see. Turns out that this wave is just describing the possible outcomes or the probabilities of seeing certain outcomes if you do experiments. Okay, so a wave of a particle just tells you, if you kind of look at this de Broglie wave or particle that is and its wave, it tells you if I would do a very precise measurement of where this particle is, this wave will tell me what the probabilities are that it's here or there or there or there. Okay, so it's a superposition. A particle can be at many, many different kind of points in space at the same time. Okay, so, and what you see is that if you kind of take this quantum mechanics at face value, probability theory is very much ingrained in it. Okay, it means that it's all about probabilities, it's about uncertainties. Okay, there's about, you cannot never make sure if you do an experiment what the outcome will be. Probability theory or somehow the chance is a fundamental element of the theory. So before quantum mechanics, when people talked, people had thought a lot about probability theory, but probabilities were always related to the fact that you didn't have the most precise description of your system. You only knew something about the system and say, okay, the probability that is this, and so further. This is how statistical mechanics was made. It was really kind of, probabilities had to do with the fact that you didn't have the complete knowledge about the system. Quantum mechanics completely changed the rules. It says, no, these probabilities or things, chance is a fundamental part of the equations of physics. Okay, so you can never say something that is completely sure. And the consequences of this are, of course, these very kind of, well, these iconic pictures that you see everywhere when people talk about quantum mechanics. For example, the double slit experiment. So this is something absolutely stunning. It means that if you take one particle, of course in this picture there's many, but if you would take one particle and you make sure that the de Broglie wavelength of that particle is larger than the distance between these two slits, and you send it through these slits, it will kind of go to the two things at the same time, and it will actually interfere with itself. Okay, so one particle can interfere with itself because it can actually go through the two slits at the same time. The only thing you have to make sure is it's cold enough such that the de Broglie wavelength is larger than the distance between these two slits, but you will see these interference experiments. So this is this famous double slit experiment from which people like Feynman said, okay, if you understand this, then you basically understand most of quantum mechanics because it's about this superposition principle. It's about the fact that a particle can be at different places at the same time. Schrödinger, who is actually made the most important discovery in quantum mechanics, could not live with this interpretation. Okay, so he actually devised a thought experiment to basically make this look ridiculous. Okay, so this thought experiment with his cat was really to say, no, quantum mechanics, this interpretation cannot be right. Okay, if you kind of take this at face value that something can be in a superposition, I can have a cat that is both alive and dead at the same time, and we obviously never see this. Okay, so for him, this thought experiment was just to say quantum mechanics cannot be right. There's something missing there. Okay, because although he discovered quantum mechanics effectively, he did not believe in the consequences. Okay, but nevertheless, it turns out that people nowadays are making things like that. Of course, not in terms of cats, but they are making macroscopic objects that are in the superposition of different things at the same time. They're interfering big molecules like buckyballs. These are already kind of quite some molecules. They interfere them through somehow these interference experiments. So these big atoms can really be in superpositions, and this turns out also to be the basis of this whole new industry that is currently kind of coming into existence. Is this making a quantum computer? A quantum computer is effectively putting many different calculations in superposition. This is like a Schrödinger cat. You're kind of doing many different calculations in parallel. Okay, you're doing many things at the same time. And that is somehow the basis of this quantum mechanics. Okay, so of course, this was Schrödinger. The nemesis of Schrödinger was Heisenberg. They really didn't like each other. But Heisenberg had actually a very nice way of interpreting somehow this superposition principle, or somehow this way of understanding why something had to be a wave. Yeah, so what he basically realized is that if you observe a certain particle with light, okay, because we all accepted now that light consists out of particles, if I look very precisely at a particle, okay, so the more precise I want to locate a certain particle, I need to use smaller and smaller wavelengths of my light, but the smaller the wavelength of the light, the higher the energy. And somehow then, if I want to look at something very precisely, this energy of this photon will be so large that it will completely kind of change the position of the particle. Okay, so that, in some sense, this gave you a very, a completely different picture of why indeed something had to be somehow uncertain. Okay, so because you can never be certain what it is, because the more, from an experimental point of view, the more precise you want to measure something, the more you will disturb it. And that is actually completely compatible with this interpretation of quantum physics as a particle being in a superposition at different places, because that's the only way of making sense of this. And this is this amazing kind of property of quantum mechanics that you can never both kind of know the position and the momentum of a particle at the same time. The more precise you know the position, the less precise you know the velocity of your particle, and vice versa. And of course, this had inspired many people, also in philosophy. It's actually very interesting that Hannah Arendt, who is of course a very famous philosopher, was a good friend of Heisenberg, and she actually kind of took these ideas and really used them in her philosophy. So this is actually maybe...
So natural science does not simply describe and explain nature. It is a part of the interplay between nature and ourselves. It describes nature as exposed to our method of questioning. This was a possibility of which Descartes could not have thought, but it makes the sharp separation between the world and the I impossible.
So this is what quantum mechanics, in quantum mechanics, you cannot just say that I'm observing the world. From the moment you observe, you change it. Okay, so this is, again, one of these very strange philosophical consequences of quantum mechanics, that you cannot, well, whenever you do something, you're part of it, and that makes it so difficult, of course, to do quantum mechanics. The really interesting things of quantum mechanics actually only come into play when you look at many particles. Okay, so you can say one particle, two particles, but what happens if you have many particles? Okay, so turns out in quantum mechanics, actually in many other branches of physics too, if you kind of start looking at many particles, completely new possibilities emerge. Okay, there turns out to be completely new worlds. Like if you kind of want to understand many particles, we still have the equations. Schrödinger basically described, the Schrödinger equation is still perfectly valid to describe your system of many particles, but the complexity of solving these equations becomes so immense that we cannot solve this. Okay? So basically all of the research since the last 100 years in theoretical physics, or at least a very big part of research in quantum physics or in theoretical physics in a whole in the last 100 years has been to try to solve these equations or to find good approximations to these equations. Okay, because we know the equations, we cannot solve them, and why can't we solve them is because they become complex. Okay, there's some kind of an exponential growth. If you kind of look at the complexity of solving this equation, every time you add one particle, the complexity doubles. Okay, this is probably the only good thing that came out of COVID, is that everybody understands now very well what exponential growth means. Okay? So every time you add one particle, the complexity doubles. Okay? And of course, we are not interested in 2 or 3 particles. We are interested in many, many particles if you want to talk about matter. And that is somehow the big question. So maybe you can go back to the previous slide. So there's this whole kind of extremely complex world, and in many ways, there's no way that we can solve these equations. They are too complex. But nevertheless, it seems nature follows some very, very clear rules. Okay? So it turns out that in nature there is this exponential complexity can still somehow kind of be channeled, can be focused such that at the end we have all matter that we see, and we can describe this and we can start understanding. Actually, all these ideas of like finding the transistor, like I talked about before, finding the band structure of a transistor, is because people realize that there's much more there's some other laws that come into play if you that are crucial to understand this many body problem. And the most important property of quantum mechanics that comes into play is actually symmetry. Okay? And so Emmy Noether, it's a German professor that is not so famous, but she made like for every physicist, she's an absolute hero. So she made one of somehow the most important discoveries, I would say, in physics. She was a mathematician, but she realized that symmetry is effectively the organizing principle in physics. That if you want to understand why are the laws what they are, it has all to do with symmetry. Okay? Symmetry is the complete organizing principle in physics, and that is what will allow us to make progress in the many-body problem.
So Noether's brilliance lies in her realization that the laws of physics governing change and motion also conceal a fundamental constancy. She uncovered the key to understanding why the laws of physics are the way they are. While Newton and Galilei displayed genius by guessing specific laws, Noether looked deeper and discovered an organizing principle behind them all: symmetry. Nearly all major breakthroughs in theoretical physics stems from discovering new ways in which symmetries manifest themselves in nature. The simplest example is Mendeleev's periodic table, where the periodicity reflects how the rotational symmetry of an atom is represented. A more advanced example of symmetry shaping the laws of nature is the Standard Model, which defines the properties of all elementary particles. This model is entirely built around a symmetry group. In essence, quantum physics is a blend of 3 vital ingredients: a pinch of symmetry, a pinch of conservation laws, and a pinch of evolving insights. The perfect recipe for a 3-layer cake. And once again, we're faced with the almost unreasonable effectiveness of mathematics. One key can unlock an entire series of doors. In this sense, Emmy Noether held a true master key in her hands.
Okay, so this was actually the really missing part about this physics, and actually it's an amazing, strong kind of idea from Wolfgang Pauli. He said that 2 particles or 2 fermions or 2 electrons can never be in the same state. Okay, they cannot be in the same wave. They cannot represent the same wave. Yeah, and this is about symmetry. It's about saying that all the particles are equal, and exactly because they are equal, they cannot be equal. Okay, so if this sounds strange, it is true, but it's about symmetry. It's about actually a property of the wave function. It tells you that because of symmetry, the wave functions that we care about have to be antisymmetric. If I change 2 particles, I need to have a minus sign. And what is amazing is that this is by far the strongest force in nature. If I push here on this chair and my hand is not going through it, this is not because of some electromagnetic force or some kind of strong force or whatever force. It has to do with symmetry. It's because the electrons in my finger don't want to be in the same state as the electron in this chair. So this is actually by far the strongest force in nature. It's what kind of keeps the Earth from shrinking to a pea. So this is a symmetry principle. Okay, the symmetries are kind of much more powerful than the actual forces. They are, because they have to be exact, they cannot be violated. It's not just a force, it has to be an exact thing, and this is what kind of makes matter what it is. Without these symmetry principles, we would not understand anything about matter. Because matter, from the point of view of classical physics, actually everything should immediately shrink. And there's nothing that kind of pulls things apart from each other. What pulls things apart of each other is this exclusion principle of Pauli. And it's all about symmetry. And that kind of insight, of course, led to a huge revolution. Everything in chemistry, of course, also this very famous kind of DNA that was also discovered here in Cambridge. The shape of a crystal. Okay, if you want to kind of understand how electrons, what the properties of electrons in a material, turns out that this completely kind of determines what the shape is of a crystal. It's completely kind of quantum mechanics has to do with these. This has to do with how the different electrons kind of fill these bands, and the electrons cannot be in the same state, and therefore they have to kind of occupy this. And this band structure of the electrons determines what the possible shapes of the crystals are that we look like. This is one of the highlights of any course in physics, namely in group theory, about symmetries. Group theory is basically the mathematical language for describing symmetries. And one of the highlights is the fact that you can prove that there's exactly 230 ways in which you can arrange a crystal. Okay, so there's only 230 ways, not more than that. And there's 230 ways of kind of making periodic arrangements of atoms. Yeah, and why is this coming and how is this kind of emerging? It has everything to do with these band structures, and the amazing thing is that every one of these 230 ways that you can prove mathematically are realized in nature. Okay, but there's of course much more. Color. Okay, like color, that is something that we all see all the time. There's nothing that we can understand about color without quantum mechanics. What is actually going on when color or when light is shining on, let's say, a green leaf, is that this has to do with the electrons in that leaf. Okay? These electrons in that leaf have can have specific energies. They are in the energy bands, and there's also forbidden energies. Okay? So there's some kind of, these electrons in this material, in this leaf, they cannot be in a certain energy band. And that means that if light comes in with a certain frequency and it would excite an electron in this forbidden energy band, it cannot kind of be absorbed. It has to be reflected. So if you see something green, it's because the material, the electrons in the material cannot absorb this kind of photon, so they have to reflect it. That is what makes something green. So whenever you see a color, it's a purely quantum mechanical process that is at work there. So nobody understood anything about this before quantum mechanics. Of course, the most disruptive discovery of the 20th century has to do with this transistor. So what did Bardeen do? He calculated what are the possible energy levels of the electrons in silicon, and he engineered then somehow this silicon and added some kind he added different impurities such as to get a perfect to make sure that these energy bands would be what he wanted, such that he was able to make the transistor. So it would have been completely impossible without understanding this Schrödinger equation, and especially the Schrödinger equation together with this exclusion principle of Pauli. Okay, so of course then physics went much further. Okay, so you could say, okay, then let's go even smaller to higher energies and so further, and then you need modifications to this. Actually, the first person to make the decisive discoveries about this was exactly this Dirac that we talked about before. Dirac is the first one who realized that if you kind of go at even kind of bigger energies or smaller scales, then you need relativity theory and quantum mechanics to merge to each other, and that's exactly what gives rise to something that's called quantum field theory. And the highlight of quantum field theory is the fact that there's this standard model that basically explains all the fundamental experiments that can be done. And of course, you probably have all seen this picture of CERN, where this huge collider to understand the smallest of the particles. And again, this has to do, of course, with this uncertainty principle. You want to kind of look at very small scales, you need huge energies. Okay, this is again somehow this duality, this complementarity that is at work here. But actually, from the point of view of physicists, going to the smaller and smaller scale, kind of this reductionism to kind of try to understand the smallest, is not really the most interesting thing. Turns out that it's not because you understand quarks that you understand biology, to make it a little bit kind of thing. So there's many different scales in between. And that has to do with this that if you kind of start putting many particles together, you can get completely new laws. And actually the first person to really kind of appreciate this, understand this, is Philip Anderson, who also was a professor here at some point in Cavendish, in Cambridge. And he was the first one to really understand that if you kind of, instead of kind of going to the smaller and smaller energy, that it's much more interesting and that you can have much more kind of relevant phenomena by putting many particles together. And trying to understand what kind of new phenomena can I get when I kind of start putting all these electrons together. Can I have some new emergent phenomena? Can I get kind of new physics? And this whole idea of emergent phenomena is actually something very interesting. What it tells from the physics point of view is that at every different energy scales you can have completely new phenomena. It's not because you understand the standard model that you can understand a superconductor. Okay? There's no way. This is the superconductor, the equations that you need for a superconductor, something very relevant in many applications, is they are completely different than the laws that you need to describe high energy physics. And it's not because you know the fundamental laws of the standard model that you will be able to predict that things like superconductors are there. And it's not because you understand basically things at the scale of a superconductor that you understand anything of biology. It's not because you understand anything about biology that you understand anything about economy. These are all kind of different scales, and there's actually an explanation for that in terms of something that's called the renormalization group. Okay, that's one of the most famous realizations of quantum mechanics in the second part of the 20th century. And Anderson was crucial there, and actually one of his students when he kind of gave his courses here in Cambridge was Josephson. And Josephson, as a student, then immediately kind of discovered the Josephson junction. And this is one of these amazing phenomena that are used everywhere now to measure kind of things much more precisely than you can with any other means. And this is an emergent phenomena. There's also another emergent phenomena that has to do with magnetism, with putting magnetic fields somewhere and then measuring the resistance. And if you kind of cool these things down such that you're sure that the wavelengths of the particles are overlapping, then completely new phenomena can exist. Yeah, these are these emergent phenomena, and this is actually what people are studying now. Nowadays, this is still kind of completely open how to kind of describe this. So, but it's interesting maybe to read another kind of small
quantum Hall
part
effect
of the book.
So on the night of 4 to 5 February 1980, at around 2 a.m., the alliteratively named Klaus von Klitzing discovered something that was never meant to be discovered, something that no theorist thought possible. Von Klitzing discovered perfection. The crux of the essence is this: no matter what material is used to perform the quantum Hall experiment, the result remains exactly the same. This is the perfection of von Klitzing. The caveat, of course, is that your sample must be large enough and, strange but true, contain small amounts of impurities. It's precisely these impurities that allow us to see the quantum Hall effect. The imperfections are not an obstacle, but a prerequisite for success, however counterintuitive that may seem. This is the power of emergent behavior. More is different. Emergence leads to the most unexpected phenomena. Here we have perfection born out of imperfection, a Greek tragedy rewritten as a triumph.
Okay, so maybe you can go to the previous slide again, because indeed, so this quantum Hall is about measuring basically the resistance as a function of the magnetic field, and you see that there's these steps, and these steps, they are clearly quantized, and this is something extremely useful in many applications, but this was something that was, it's perfect, okay? These steps are always exactly where you want them to be, independent of how much imperfections you have, and this is one of these hallmarks of emergent phenomena. By knowing just how the standard model works, you will never be able to predict this. It's only by putting many particles together, all these particles start working in unison together, such as to create these phenomena. And actually, this is exactly the technology that we want to use to kind of create new materials. And this is exactly the topic of the second quantum revolution that is currently kind of going on. So for the moment, we are kind of, so the first quantum revolution happened 1900, 1925. Discovery of quantum mechanics, discovery of the Schrödinger equation, all the applications in chemistry, in material science, and so further. But nowadays, there's a complete new revolution going on, because it turns out that we can start controlling and manipulating individual atoms. This was only a distant dream somehow that happened 100 years ago. For them, quantum mechanics, for people like Schrödinger, all these equations were just some equations. You would never be able to see an individual atom or an individual photon. But nowadays, people can actually control this. There's so much experimental kind of progress. So this is actually a picture of a lab here in Cambridge. You see, this is amazing, kind of the number of optical components you need to make one of these experiments by which you can see individual atoms. But somehow by creating these individual kind of atoms and manipulating them, suddenly you can actually create also new emergent phenomena, such as, for example, a quantum computer. A quantum computer would allow you to do things that you cannot do with any other means. Okay? And it turns out that the key element or the key theoretical idea has to do with entanglement. Okay? So if you kind of start being able to manipulate these individual atoms, you will also be able to entangle them, to make quantum correlations between them that are very, very different than classical correlations. Okay? Turns out that this is one of the fundamental ideas. Also, Einstein, again, was the first one to realize that this had to exist. He didn't believe it. He used this idea of entanglement to say quantum mechanics cannot be complete, cannot be the right theory, because it's so strange. If you have an entangled state, and I have like an entangled state of two particles, if I do a measurement here, instantaneously it has an effect somewhere else. And that, at first sight, would completely violate, of course, the principle of relativity, that nothing can travel, no information can travel faster than the speed of light. It took a long time for people to understand that this is not in violation with that principle. It's not because you have entanglement that you can actually send information from A to B. If you kind of do a measurement here, it has an instantaneous effect there, but it cannot be used to send information. And that kind of, these ideas of merging quantum mechanics with information is again coming up here. This is something that, of course, Einstein could not have known at that time, and that's why he was very worried about it. But nowadays, this entanglement forms the basis. It gives you a new language for doing physics. Okay? So as I said, the biggest problems or the biggest kind of research topics in theoretical physics have always been, how do I describe quantum mechanics of many particles? How can I deal with more and more particles? And we were stuck. Okay? There's some kind of tools known for this, but nobody really understood this. And because of the advent of this new quantum revolution, people have realized that entanglement is the key in understanding and kind of these phenomena, the many particle phenomena. And this entanglement is leading to a completely new language for doing physics. And of course, if you have new language, you need the vocabulary, but you also need the semantics. You need somehow, there's a completely new way of looking at physics. And even quantum black holes, okay? Turns out that, okay, you see, this is a black hole. Turns out that this is nowadays, people kind of try to kind of look at this from the point of view of this entanglement. Turns out that this new language of entanglement and quantum correlations is exactly kind of the right way of understanding these phenomena. Okay, so what is one of these main insights, and Richard Joseph, who's also a professor here in Cambridge, was very instrumental in understanding this, is that entanglement is basically a resource. That if you create entangled states, if you kind of look at entangled states, these particles that have very strange correlations, you can start doing things with them that you cannot do without them. Okay, so for example, you can start doing teleportation. You can take two particles and actually do measurements, and instantaneously the properties of that particle are teleported somewhere else. And like this, you can distribute all these entanglement between many, many particles and create extremely interesting states by which you might actually be able to do interesting things. And this is exactly the topic of quantum computing. And quantum computing is nowadays one of the hottest topics in the field of theoretical physics. This is an actual quantum computer. Of course, a quantum computer is still kind of in a very experimental stage. They can only kind of they can only entangle, let's say, maybe 50 or at most 100 qubits, they call them, with each other. To do really interesting things, we need many more. But you start entangling, you start creating states of matter that are very, very different than the states of matter that you would see in nature. And these states of matter allow you to kind of do things that are very different. So these are, for example, with a quantum computer, you can solve problems exponentially faster than with the classical computer. And why is this? Because this quantum computer, this entanglement, can be used to do many, many different calculations in parallel. Okay, you do one calculation with a computer and another one. With a quantum computer, you can start doing these things in parallel. And for example, one of the most famous problems that was solved by Peter Shor was the factoring problem. Okay, so the factoring problem is just a purely computational problem. I give you a large number, an integer, like 323, and I ask you, what are the factors of that number? Okay, so this is the smallest number for which is not obvious. Okay, most numbers that are smaller, it's immediate. But it turns out that this is very hard. Okay, if I give you a very large number, it's very hard to find the prime factors. Okay, so it turns out that 323 is 17 times 19. Okay, but it's difficult to guess this. And if you have a very large number, then it's extremely hard. It turns out to be exponentially smart in the number of digits. And this complexity is actually the basis for all cryptography. Whenever you use the internet and you exchange information about your bank account or something, the security of that is guaranteed because it's very hard to factor large numbers. This is everything that is sent on the internet when you send information. It's based on the complexity of this. Turns out with a quantum computer, you can actually solve this problem in polynomial time. So from exponential to polynomial. So a quantum computer would be able to solve this very efficiently. Fortunately, there are no quantum computers yet that can do this. Okay, why? Because you wouldn't need a quantum computer with something that is in the order of 1,000,000 qubits. Okay, so for the moment, the largest computers are quantum computers that are there maybe have 50 qubits. Okay, so there's still a very, very long way to go to scale these things up, but at some point we will be there. And so why is it so hard to build a quantum computer? It turns out that this has to do with decoherence. Okay, it turns out that it's extremely difficult to isolate a quantum system from its environment. Okay, so a classical system is very easy to isolate from an environment, a classical computer, because a bit is 0 or 1, and if you want to kind of isolate it from the environment or protect it against noise, you just make copies of it. 0, you code it as 0, 0, 0, and 1, 1, 1, 1, and there's some kind of a systematic way in which you can do this. A quantum system, because of its very nature, can be in a superposition. It's much, much harder. Can be in many in a superposition of many different values. It's much, much harder to protect this against noise. And quantum systems are very sensitive to noise. So what is noise? It's, for example, light. If you have an experiment, and there's some light source or a gamma particle falling in your experiment, it will entangle itself with the experiment, and it basically will make sure that the computation that you do is screwed up. So what is somehow this problem is indeed this decoherence. So how do you, this is the fundamental problem that that people are tackling for the moment in the field of quantum computing. And indeed, if you kind of see the highest kind of cited papers in physics of the last year, these are papers about this problem, how to kind of protect quantum systems or this quantum memory, so how to kind of create these qubits that are protected from the environment in terms of something that's called fault tolerant or quantum error correction. And what is extremely interesting is if you see at these papers, where are these papers written? It's IBM Quantum, Google Quantum, yes. So this whole field of quantum computing has actually become such a humongous enterprise that no university can do it anymore. You need kind of teams of thousands or hundreds of people to actually work on them. You need extremely expensive kind of apparatus to do this. So the only kind of companies that, or the only place that the real kind of biggest developments are being done for the moment is in indeed these very big companies about quantum. And I'll have to speed up. Okay. Okay, but anyway, so what?
Almost there.
What could you do with a quantum computer? Or why is a quantum computer? Why do these companies invest in this? What will you be able to do with a quantum computer that you cannot do before? As I already said, the biggest problem in quantum physics and theoretical physics is solving the many-body problem. So why is this so hard? Because somehow, if you would solve this, you would be able to kind of do much better quantum, you would be able to do chemistry much better. You would be able to design better catalysts. What is the bottleneck in designing more efficient catalysts for many chemical processes? It's because we don't understand the structure, we don't understand the electronic structure of these atoms. We don't understand how the electrons, basically what is the wave function of the electrons in these molecules. And we don't understand this, but a quantum computer would be able to do this in a very efficient way. So another problem that people have broken their heads off for now 50 or more years is how is it possible to design superconductors at room temperature? Okay, there's no reason why we would not be able to make a superconductor at room temperature. And if you would have a superconductor at room temperature, that would mean that you can conduct electricity without friction, without heating up. Okay, so your cell phone would not heat up if you kind of use it a lot. That would mean that instead of kind of being able to use it one day, you would be able to use it 1 month. So this would be one of these extremely disruptive discoveries to find a material, to design a material that is superconducting at room temperature. What is the reason that we cannot do this? We cannot do this because we don't understand the electronic structure. We don't understand the entanglement that is going on between the electrons in the materials that would allow to do this. So superconductivity is one of these emergent phenomena. It's one of these things in which all the electrons work together, and we cannot solve these equations. And a quantum computer would be a very kind of, with a quantum computer, we would be able to solve the Schrödinger equation for the many particle problem. And you can kind of go on, you can start looking at drug design, many other things. This is the reason that people want to build quantum computers, not to factor problems or to read your emails. Quantum computers would kind of be used to make really kind of lots of new discoveries, both in drug design and chemistry and material science and many more.
So to conclude, as you can see, quantum mechanics was not invented by just one very smart person in his ivory tower. It's really like a relay race of very smart scientists who worked together, who collaborated, who questions themselves, and you see here one of these main characters. And I found it quite important also to pay a lot of attention to women in science, because everybody of course knows Marie Curie, but there was Emmy Noether, there was Lise Meitner, there were so many interesting women in science that also are worth talking about, and they're also included in the book. So I hope that the book can be some kind of an ambassador for young girls for studying science, because they are, of course, as smart as boys and as capable as young men. So this leads us to the final conclusion that we can say quantum mechanics works. No theory of physics has ever had such spectacular success. From ignorance about the structure of matter, quantum mechanics has brought us in less than a century to an understanding so broad, powerful, and precise that virtually all contemporary technology relies on it. And the theory has enabled us to make sense of phenomena far beyond anything technology has yet been able to exploit. And this, despite the fact that nobody understands quantum physics. And a little final a haiku that has been written especially for our book, and I think it's the best conclusion that we can give, is: the invisible uncovers the visible. Knowing more brings joy. Thank you very much.